So neutralization reactions, really the only thing new with this is the vocabulary. It's all stuff we've done before, and in fact, most all of you are pretty good at. A neutralization reaction is any chemical reaction that happens between an acid and a base. Anytime you have an acid reacting with a base, it is by definition a neutralization reaction. Now, usually, that is a double replacement reaction. It doesn't have to be, but usually it is, in fact, a double replacement reaction. And usually, we are trying to make the resulting solution a pH 7 or a neutral. And that's why the term neutralization reaction, because the resulting solution is a pH 7 or a neutral solution. Okay? As I said, we've done this all before, just with a new name. That's all. It's actually stoichiometry. That's really what it is. It's just stoichiometry between acids and bases. So if we take a look at this question that I've got here, what volume of 0.50 molar nitric acid is needed to neutralize 25 milliliters of 0.35 molar sodium hydroxide? That would typically be how a question like this might be phrased. What quantity, what concentration, what amount do you need to neutralize? Now, when we say neutralize, remember we're trying to get to a pH 7 solution. So when we neutralize something, what we mean is we want to completely react it. We don't want any acid left. We don't want any base left. We want neutral. This is, at its heart, simply a stoichiometry problem. We have information about one substance, but we want to know something about a different substance. That's what stoichiometry is. So, of course, we do need to have a balanced relationship, a balanced chemical equation for this system. And we do have two materials here. We have nitric acid. That's a formula you should know, HNO3. And it is aqueous. And that nitric acid is to react with sodium hydroxide. Well, we should be able to write the formula for sodium hydroxide. Sodium is Na, it's ionic. One valence electron, it loses it, plus one charge. Hydroxide is an OH group with minus one charge, plus one, minus one, we're good. And that is also an aqueous substance. Solution. So when these two things react, what pattern of chemical change do we have here? And this is a double replacement reaction, isn't it? We've got an ionic pair, and they switch, don't they? In the double replacement reaction, we switch the positive ions. That's what we do. And it's a double replacement reaction. We've done this before. We've done this dozens, hundreds of times. And so the hydrogen winds up with the hydroxide, and the sodium winds up with the nitrate. Of course, we check our charges to make sure that the molecules are good. Plus one, minus one, that's a good molecule, HOH. Plus one for the sodium, minus one for the nitrate, plus one, minus one, that's a good molecule as well. We're good with our formulas, aren't we? Then we balance the equation, one hydrogen, one nitrate, one sodium, one hydroxide, one hydroxide. Hey, we're balanced. We do need to put states of matter on it. Well, HOH, liquid, right? Water is usually a liquid, except for combustion reactions, and this isn't combustion. And sodium nitrate is ionic, there's water present, and so it is aqueous. Now I have a correctly written balanced chemical equation, right? This is a double replacement reaction. It's also a neutralization reaction. Nitric acid is an acid. And what is it that acids do? Well, Bronsted-Lowry tells us acids donate hydrogen ions. That's what they do, right? So the hydrogen nitrate, the nitric acid, is donating a hydrogen ion. Well, where does the hydrogen ion go? It goes to the sodium hydroxide. And so the sodium hydroxide is accepting the hydrogen ion, which makes it a base. See, it's an acid-base reaction, and so it's a neutralization reaction. Of course, we could go crazy here, and we could go label the conjugates as well. Remember, the conjugates, we look at the reaction in the reverse direction. And so in the reverse direction, the water would be getting rid of the hydrogen ion, so that would make it the conjugate acid. And the sodium nitrate would be receiving the hydrogen ion in the reverse process, so that would make it the conjugate base. All right. We could label them. It's not really necessary for this question, but I'm trying to illustrate and explain why this is a neutralization reaction. Any reaction between an acid and a base is a neutralization reaction. Whether we run it all the way to 7 or not, whether it's a double replacement or not, if you've got an acid and a base reacting, it's neutralization. But it's usually double replacement and usually to completion. That is neutralization, a neutral solution. All right, now that we've got our balanced chemical equation, let's go deal with the question at hand. So I need to find moles of something, because that's what we do in stoichiometry. We get a balanced chemical equation, and then we go find moles. So what is it that I'm going to find moles of? Well, I'm given information about the sodium hydroxide. I have a volume and a concentration. So I'm going to go find the moles of solute over liters of solution. And I'm going to use the information from the sodium hydroxide because I have two pieces of information there. I have a concentration, 0.35 molarity, and I have a volume, 25 milliliters. Of course, I need that in the form of liters. So I need to change milliliters to liters. If it bothers you that I'm doing this in one step here, where I have my conversion inside the equation, if that bothers you, then by all means do it separately. I'm doing it here because I'm trying to save space on my board right now. So when I do this fancy math here to find moles, 0.35 times 0.025, I get 8.75 times 10 to the minus third moles of sodium hydroxide. Because that's the information that I have moles for. Of course, now that I have moles, is this the material I'm interested in? No, that's nitric acid. And that's why I needed the balanced equation, so so that I could convert my moles of sodium hydroxide to moles of nitric acid using the balanced equation. And in this case, it's a 1-to-1 system. Well, that makes the math really easy when it's 1-to-1. Because then I need 8.75 times 10 to the minus third moles of hydrogen nitrate. Does that answer the question, though? No, it doesn't answer the question. The question asks what volume of a solution, and that's not a volume, that's moles. Well, we need to go answer the question then, what volume of the solution? Well, I'm going to need to use molarity again. Moles per liter. This time, though, it's for the nitric acid. 0.50 molarity. 8.75 times 10 to the minus third moles. And I'm going to go find my volume then. And when I do that fancy math, 1.75 times 10 to the minus second liters. Let's see, I've got 2 significant figures, 2 significant figures, 3 significant figures. I'm going to be allowed 2. My best answer is 1.8 times 10 to the minus second liters. It didn't specify milliliters, so I can leave it this way. Yeah, I need 18 milliliters. I need 18 milliliters of this half molar nitric acid to completely react with 25 milliliters of 0.35 molar sodium hydroxide. It's a stoichiometry problem. Just happens to be a stoichiometry problem between an acid and a base. It's no different than if it's solids, liquids, aqueous, gases. We can deal with any state of matter that we need to. We can deal with any kind of chemical reaction that we need to in this stoichiometry process. But because it is between an acid and a base, we call it neutralization so as to try to confuse people. It's the same chemistry we've done. There is nothing new here on the board other than the term neutralization. So don't freak out about it. Now, there is another way of dealing with neutralization. You don't always do it. In fact, usually and most of the time, stoichiometry is the quick and easy way to deal with it. Because with stoichiometry, we're real comfortable dealing with it. We know how to. But we have to know the identities of the materials. We have to know what they are so that we can find the relationship. There is another way where the identity is not necessary. And that's really where pH can be used. Remember, Zoran Zoranson developed his idea of pH, this pH concept, for a purpose. In his case, he was trying to understand the process of what happens in water in order to understand what's going on in the process of manufacturing beer. Zoran Zoranson was a chemist for the Carlsberg Brewery. And so they were trying to standardize, try to figure out really what's going on. pH scale, remember 7 is a neutral, right? 7 is neutral. Any value that's smaller than 7 must be acid. Any value larger than 7 is a base. And no, there is no end point on it. In fact, on your worksheet for pH, there were a couple of examples where you calculated pHs above 14 if you did it correctly. There was even a case where you came up with a negative pH if you did it correctly. It's okay, it's a number line. You just keep right on going. What it's telling us about is concentration, right? That's what pH tells us, concentration, specifically of hydronium. And as we move around on the scale from one number to another, that is, we make a step on the scale, the concentration of that ion changes by a factor of 10. As you move away from 7, the values of concentrations get bigger by 10. As you move towards 7, the concentrations go down by 10. So here I have some containers of liquid, and they're labeled with various pHs. So let's take a look here at this pH 8 for a minute. Here's a solution, here's a container with a certain amount of pH 8 in it. So pH 8 tells me it's a base. The number's bigger than 7, it's got to be a base. And what do bases do? Bases accept hydrogen ions. That's what bases do. And so a really good example of a base, a really good base, would be hydroxide ions. Because hydroxide ions are going to grab onto a hydrogen ion and make water, right? Hydroxide is a base. So let's imagine that in this volume of solution, there are 2 hydroxide molecules, 2 hydroxide ions floating around in there. There's probably thousands of them. We'll just, for our visualization, I'm going to draw 2 of them, okay? That inside of this container, at this volume, whatever that volume is, maybe it's 10 milliliters. And all of these are 10 milliliters. That there are 2 hydroxide ions floating around in that 10 milliliters of volume. Well, what would a pH 9 look like then? Is it more concentrated or less concentrated? It's more concentrated. How much more concentrated? 10 times more concentrated. Every step is a factor of 10. So in here, there's not 2 hydroxides. There's actually 20 of them. 10 times more. I've got a lot of hydroxides to cram in here. There are 20 hydroxides in there. In that same volume. Why? Because it's 10 times more concentrated. Okay, so what would a pH 10 look like? It would be even more concentrated. How much more concentrated? 10! 10 times more concentrated. Each step is a factor of 10, right? So there are now 200 hydroxide ions in here. It's gonna be really crammed in here. Just lots and lots, right? Just hydroxides everywhere you look. There's so many so much hydroxide. So many hydroxides. 200 hydroxides. What would a pH 11 look like? A 12, a 13, a 14, a 15, a 16, and so on, right? Each time getting 10 times more concentrated. All right, let's go to the other side. Let's go over here to a pH 6. pH 6 is an acid. It's less than 7. Acids are things that donate hydrogen ions. So acids would be represented by hydroniums, right? Because they're going to donate a hydrogen ion. And since I have 2 of them here in a pH 8, I'm going to put 2 of them here in a pH 6. Right? They're equidistant from 7, so they should be equal concentration. So what's a pH 5 going to look like? Yeah, it's going to have 20 hydroniums in there. What's a pH 4 going to look like? Yeah, it's going to have 200 hydroniums in there. What's a pH 3? A pH 2? A pH 1? A pH 0? A pH -1? A pH -2? A pH -3? Yeah, it just more and more and more hydroniums in there. How many more? 10 times more, right? Every step you take. Does it matter whether that's sulfuric acid or nitric acid? No. Does it matter whether that's acetic acid or nitric acid? Nope. Just hydroniums. The identity doesn't matter. So, in my little diagrams where I'm trying to illustrate this, let's say that in every single one of these containers I have exactly 10 milliliters. Right? They're all the same volume. So let's imagine that I have 10 milliliters of a pH 9 solution. That's what I have. I have 10 milliliters of a pH 9 solution. How much pH 5 solution is needed to neutralize it? See, I don't actually need to know what the materials themselves are this way. I just need to know what pHs I'm working with. Well, if in my 10 milliliters here, I've got 20 hydroxides, right? And over here in my pH 5, I have 20 hydroniums. What volume do I need? The same volume, right? Because they're equidistant from 7. If I have 10 mils of this, to get it back to 7, I need 10 mils of that, don't I? Whoop! I would need 10 mils. That's kind of sweet. Okay, how much pH 4 solution would I need to neutralize it? So I've got some pH 9, I've got 10 mils of pH 9. And I've got some pH 4 solution laying around. How much pH 4 should I put into that pH 9 so that it's neutral? Well, are they equidistant? No. Am I going to need more 4 or less 4? I'm going to need less of it. How much less? 10 times less. Why 10 times less? 1, 2, and I'm off by a factor of 10, aren't I? You can just count them out. Instead of having 10 milliliters, I actually only need 1 milliliter. That's pretty crazy, huh? Hey, what would happen? What would happen if I took 10 milliliters of 9 and 10 milliliters of 6 and put them together? What if I put 10 milliliters of 9 and 10 milliliters of 6 together? Would it be neutral? No. Why not? Because you got a lot of base here, don't you? You got 20 hydroxides and you've only got 2 of those. You put those together, you're going to have 18 hydroxides left, aren't you? You're going to be in here, right? Probably like pH 8.9. Right? Every step is a factor of 10. So if I had pH 6 around, how much pH 6 solution would I need to neutralize my 10 mils of 9? I need 10 times more, don't I? Yeah, I'd need actually 100 mils. You're kind of doing stoichiometry without doing any stoichiometry at all, because you don't actually need to know what the materials are. You just need to know their pHs. How do you turn a pH 9 into a pH 8 if all you have is water? Huh? Add 10 times more water, right? You'll dilute it. How do you go from a pH 9 to a pH 10 without adding anything? Take some water out, right? Evaporate it. When you reduce the volume by a factor of 10, it'll be a pH 10. It's kind of neat. Again, this will work if you have pHs, or you calculate pHs for things, but if you don't have the pHs, don't go calculate them to do it this way. If you don't have the pHs, well then, you have to know what the materials are to go calculate those pHs. Why not just do it by stoichiometry at that point? You kind of pick and choose which way, depending on the situation. All right.